Hello, this is Tom. Um, here we are for our next class in the Science and Christianity series, General Relativity and Cosmology, Part 1. Um, our verse today is Isaiah chapter 40, verses 21 and 22. Have you not understood from the foundations of the earth? It is he who sits above the circle of the earth, who stretches out the heavens like a curtain, and spreads them out like a tent to dwell in. We'll return to the verse later in the discussion today, but um, to get started, we need to draw on a few past topics as a reminder um, so we can launch into the new material. Um, First and foremost, since we're going to extend it, we need to review relativity as we've studied it to date, including a little Galilean and also special relativity. After we map out general relativity, we'll be prepared to talk about cosmology a little bit because that rests on general relativity and quantum mechanics and of course astronomy. Um, so with that, um, let's go ahead and get started. Um, we have the original concept of relativity. We first talked about during our Renaissance physics class, uh, so-called Galilean relativity, a time-honored part of physics, all the way until the modern era. So a reference frame is a point of view, and it's what motion is measured relative to. So, for example, if we have Galileo on the shore not moving and he's watching a ship that is moving at a constant speed v to the um, east, um, you know, we can say that he has a reference frame, a frame of reference, a point of view, and he can measure the velocity of the boat. But it's also possible to think of ourselves as someone on the boat, and we could also look back at Galileo, and so we would have a different point of view. But as long as we weren't accelerating, we would still observe the same physics. Okay, and whenever the reference frame we're in is itself not accelerating, that's called an inertial reference frame, because since it's neither speeding up nor slowing down, apparently there are no forces being applied to the reference frame. Now the reference frame is still able to observe forces being applied to objects, and so you can still see objects being accelerated from an inertial reference frame, but the reference frame itself is not inertial. Okay, all that said, let's remind ourselves about Galilean relativity. So the idea is, if Galileo um, is looking at a boat that's going 10 miles an hour to the east, and suppose on that same boat we have people playing ping pong on the boat, knocking the ping pong back and forth at a speed of 5 miles an hour to each other. Um, they would say that the ping pong is traveling 5 miles an hour, but if we ask, what does Galileo see? Well, when the player on the left bangs the ping pong to the right at 5 miles an hour to the right, Galileo would perceive that the ping pong is moving 15 miles an hour. He would see that the person or the two people playing ping pong who are standing still in the boat, just knocking the ping pong back and forth, they're actually traveling the speed of the boat. So when the person on the left hits the ping pong at 5 miles an hour toward the person on the right, as far as they're concerned, in their reference frame, Galileo would say, well, now the ping pong is moving 5 miles an hour faster to the right, to the east, than the boat itself, than the player who hit it. So the ping pong is actually going 15 miles an hour to the east. And similarly, when the player on the right knocks the ping pong back toward the left to the other player, although the players would think that the ping pong ball is now going 5 miles an hour to the left, right? Based on their frame of reference, Galileo would say, oh, well, gee, the boat is going 2 miles an hour to the east, except the ping pong ball, relative to the player who's moving with the boat, is going in the opposite direction, 5 miles an hour. So to Galileo, the ball would appear to be going 5 miles an hour to the west. You know, the 10 miles an hour to the west, or to the east, I'm sorry, the 10 miles an hour to the east that the boat is going, minus the 5 miles an hour to the west that the ping pong ball is going relative to the boat. So for a net total of 5 miles an hour to the east. So that's the concept of Galilean relativity. So let's look at a few examples of some different reference frames. Um, some of these are inertial reference frames, which are not accelerated. Others um, don't fit into that category. Okay, so in the first case, let's suppose you're on an elevator and the elevator isn't moving. Um, then that's an inertial reference frame. The elevator is not accelerating. And if you happen to be on a scale, it would measure your true weight. Okay. Then let's suppose the elevator begins to move upward. So while the elevator is picking up speed as it starts upward, you would not observe the same physics. Um, because the elevator has to push, the floor of the elevator has to push harder on your feet in order not only to keep you in place but to actually accelerate you upward. That means that the scale is going to read more than your true weight. So the physics in an accelerating elevator would be different. However, once the elevator reaches speed, and that's indicated by the third frame there, once the elevator reaches constant speed, we'll assume it's a nice smooth elevator. Well, at that point, once again, you would observe the same physics as we originally observed in the stationary elevator. Everything would seem the same. You would seem to weigh the same, things would behave just as they did before. And finally, in the fourth frame, let's say the elevator is beginning to slow down because it's going to stop at a floor. The elevator slowing down is another way of saying the elevator is experiencing a negative acceleration, what people call a deceleration. And in that case, you would actually not seem to have your actual body weight. You would feel just a little bit lighter for a second. So the first and the third cases are inertial reference frames. The elevator is maintaining a constant speed, perhaps zero speed. It's not changing direction. But in the second and fourth examples, that would be what we call a non-inertial reference frame because there is acceleration involved. Well, along with Galilean relativity, and I think we might barely have mentioned it, came the assumption that time pretty much flows at the same rate for everyone, everywhere, and just an everyday understanding of time, an everyday intuition, an everyday feel for time, um, almost makes it hard to imagine anything else. How could it be otherwise? So that's built in as one of the assumptions of Galilean relativity. And then worth noting also, gravity in classical physics is just another force. There's nothing special about gravity um, relative to other forces. Uh, um, any force can accelerate a mass. Gravity can accelerate, uh, you know, a rock or anything else, just like um, the electromagnetic force, just like pulling on a rope. Gravity is just another force. It's also worth noting here that Isaac Newton came up with the classical formulation for gravity. We called it his universal law of gravitation. It explained everything from um, how a ball thrown on Earth takes the path it does, to um, why the planets in the solar system actually follow elliptical orbits. So it was well received. It was considered a triumph in its day, and yet Newton himself was somewhat uneasy about it. Newton understood that he was describing what gravity actually did, not how gravity did it. He was uneasy that there was no mechanism, and it appeared that gravity, like for example, the sun's gravity, um, affected the planets to travel in orbit around it across vast distances without any apparent connection between them. So Newton always thought there was more to that story, and as we'll see today, he was right. Well, even though Newton was not entirely satisfied with his explanation of gravity, as long as Newton and the rest of physics was concerned, um, that was the only problem. Um, Otherwise, gravity was fully explained, and it was still just a force like any other, and time marched on until Maxwell happened. When James Maxwell showed that light was an electromagnetic wave that always had to move at an impressively fast speed we call c, but exactly that speed all the time, at least in if it's traveling through space, um, without so much as any medium whatsoever that they could find, like no, like any kind of mysterious ether that might fill space. Um, you know, they then the only logical possibility seemed to be that light had to move at this speed c, no matter who was looking at it, which is, of course, what um, caused Einstein to analyze the consequences of that assumption, and that's where special relativity comes from. So just to review that a little bit, let's look at a picture that a picture that we used earlier in our class. Suppose you have a train with a fixed velocity of 10 miles an hour traveling to the right or to the east. Okay, so 10 miles an hour. And let's suppose there's a person on top of the train, who is stationary with respect to the train. So in other words, that person relative to the ground is moving as the train 10 miles an hour to the right. Let's suppose the person is holding a flashlight and turns on the flashlight. The question is, what is the velocity of the light relative to the person on the train? Well, clearly, if the person on the train always observes the speed of light to be c, then the speed of light must be c relative to that person. Um, However, if we also ask the question, what velocity is observed by someone on the ground next to the train for the light that is coming out of that flashlight, that's where things seem a little trickier, because instinctively we almost want to say what would have been said according to the notion of Galilean relativity. We almost want to say, well, since the person's moving 10 miles an hour to the east, and since the light is moving c relative to that person, then clearly the light must be going, whatever c is, plus 10 miles an hour to the east. And that's not uh, what Einstein's interpretation of Maxwell's equation said. Einstein said, no, we have to say that the person on the ground also sees the light moving at at that same speed, c. Okay, they also observe light to move at c. both the person on the train and the person on the ground think the light is moving with the same velocity, okay, or the same speed. So that is where things become very different. So, for example, can the person next to the train and can the person on the train, so the person on the ground next to the train and the person on the train with the flashlight, will they even agree how far the light has gone in a certain amount of time? It turns out, and we studied all this before, that they will neither agree on um, distance nor time, nor will they agree on how far the light has gone, um, you know, at any instant. Uh, so the question is basically they will have different notions of distance and time, so that they both do observe the same speed for light. And we established this last time in part by considering this thing called a light clock. So I hope you guys remember that. Let's suppose this light clock is on the train. The essence of time dilation is that every time this little pulse of light bounces up and down between mirrors A and B, so full round trip from A to B and then reflecting back from B to A. Each one of those little pulses of light um, that goes up and then down again, that's going to be one tick of our clock, um, and so um, that's fine. But if a person on the ground, not moving relative to the train, a person on the ground seeing the train in relative motion, if a person on the ground looks at the path that the light took, um, they're not going to see that the light traveled straight up and down from A to B and then B to A. They're going to see that light took a different path, because when the light starts from A, um, the train and the light clock on the train are moving to the right. And so by the time it reflects, um, the light must have taken a diagonal path. So the path does not look the same to the person on the ground. And likewise, when it reflects from B back to A, since the train is moving and A is moving all the time that the light is reflecting, from B to A. After it's reflected from B, but on its way to A, the train keeps moving. So the path looks like the one shown on the right. So the total path traveled by the light pulse in the first case is like, um, you know, um, well, it's 2 times L, which is the distance between the mirrors divided by C. That's because we know that speed is velocity times time is distance, or distance divided by velocity is time. So it travels this distance 2L twice, and it travels it at velocity c. So the time it takes for each tick of the clock on the left is 2 times L divided by c. On the right, we can see that it would not be 2 times L, it would be twice d the light is traveling, where d is the actual length of the path from A to B and also from B to A. And it's clear from geometry that d is bigger than L. So according to a person on the ground, um, observing the light clock on the train, each tick of the clock on the train will take 2d divided by c time, and that's going to be a bigger number than 2l divided by c. So basically, time on the train is going to appear to be slower than time on the ground, which is quite shocking, but that's what you end up with when you decide that everyone has to see light moving at the same speed. And last time, from that, we were also able to figure out that for a person on the ground, things on the train would look shortened in the direction of travel. So we were also able to established that. So special relativity taught us that on a moving on a on a, if something if we're in a kind of an inertial reference frame ourselves and something is moving relative to us, they're going to experience uh, what we call time dilation. Their time is going to move a little slower. um, if we look at the length in the direction of travel of this object, it's going to appear a little shortened because of its motion in the at least shortened in the direction of motion along that it's going to appear shorter along that dimension. um, and these effects are not going to be very noticeable until we get to an appreciable fraction of the speed of light. And you can kind of see from the graphs, the one that's on the left, how the flow of time is affected as we get like very close to the speed of light, say 9/10 the speed of light. uh, Time is actually flowing less than half as fast on the moving vehicle as we're observing from our reference frame. Um, Similarly, um, the lengths that we observe on the moving vehicle, whatever it is, they become considerably smaller than they actually are to us. If we get to 9/10 the speed of light, we would only see things between 4/10 and a half as long as they actually are in the direction of motion. Um, and likewise, we could talk about, the energy of something. We talked, again, all this is review. As we get close to, as we increase speed, our kinetic energy increases. We also have our, the energy of our rest mass, whatever our proper mass is times the speed of light squared, that's equals mc squared. So if we add that to the kinetic energy, we get our total energy. But as if we are observing something, as it gets closer and closer to the speed of light, we're going to um, find that it takes increasing amounts of energy to speed it up even a little bit more. And that all means that the kinetic energy gets arbitrarily large. So it literally becomes infinite by the time you reach the speed of light if you started with something that had mass in the first place. Um, Another way to look at that is down at the bottom on the right, relativistic mass. As we approach the speed of light, the apparent mass of the object becomes enormous, and even goes off to infinity as we approach c, the speed of light. And in similar fashion, the momentum, which is just the apparent the apparent mass times the velocity, it gets enormous too and blows up near the speed of light, which is why we say that it's impossible to speed up something that has any mass to even the speed of light, because the closer you get to it, the harder it is to speed up a little bit more, and it essentially takes infinite energy to get it there. You'd have to, conservation momentum still applies. You would have to transfer infinite momentum to it to change its momentum to achieve that, and its mass would become, its apparent mass would become infinite. So none of that is really thought to be possible. So that's all review from last time. Here's another thing we talked about last time. We talked about the Doppler effect for sound, which we might have experienced in everyday life. So, like, if we're standing on a sidewalk and an ambulance is approaching, um, we might observe that it seems to have a higher pitch compared to after it passes us by and now it's going away from us. Okay, so there's a shift in the apparent sound um, that is an effect of its motion relative to us, and we call that the Doppler effect, or that we say there's a Doppler shift in the sound frequency. And we talked about that last time because we want to compare it to something similar that happens with light, which is why I'm including the review. Indeed, Same thing happens with light, and that's really what I want to remember. Um, as as something is approaching, if they're shining light in your direction, you will actually see that light appear to have a somewhat higher frequency. So it will shift a little bit toward the blue end of the spectrum. Um, Now, after it passes by, just like the ambulance, you will observe that any light coming from it now shifts in the other direction. It would appear to be more red. Things will shift toward the redder end of the spectrum. So it's very analogous to what happens with sound, which we've probably all directly experienced. Now, as as far as the speeds we encounter here on Earth, we would not noticeably um, detect the shift in the light frequency just with the unaided eye, which is why it's nice to have the sound analogy, because we can certainly detect the frequency change with our ears when the same kind of thing happens. Okay, so that's the Doppler shift for light. We'll be talking um, about shifting the frequency of light today, so that's good to review. And so that's our review of um, special relativity, and um, it resolved the issue that Einstein tried to resolve, which was to reconcile what Maxwell's equations said, what the wave equation said about electromagnetic waves traveling at the speed c. So as long as you're starting off from a good old inertial reference frame, as you would, in classical physics, and as long as you can just apply physics to all the forces and accelerations you see, except you have the nice special relativistic adjustment to make, which has been experimentally confirmed many times, then you're in business, right? Now you've taken that into account, and your physics otherwise can continue, and you can see the same physics from different inertial reference frames, and so your physics is complete, right? Yes, well, kind of, but not entirely. We have to factor in one more thing. Okay. Um, After Einstein's special theory of relativity, increasingly people began to see the speed of light not only as the speed light moved at, and not only was it a speed limit for um, any kind of object with mass, but they began to actually think of the speed of light as like the speed of causality, or at least the maximum speed of causality. Because let's suppose in this particular moment something is affecting me right now. Well, I know that whatever is affecting me right now, uh, if that's something that's affecting me happened a particular period of time ago, it must be no further away. It must have been no further away when it started out than whatever distance light could travel in that same amount of time. Okay, so anything that was further away a minute ago than light could travel in a minute couldn't be affecting me now. Anything affecting me now um, that happened an hour ago would have to be no further away than the speed of light can move in an hour, because it takes an hour for any effect to propagate, um, you know, through time, and or it takes it ta- you know it any effect that happens cannot travel to affect something else in another place faster than the speed of light. That's what it says. So not only is the speed of light kind of a speed limit for mass, but it's a speed limit for causes, right? And so Okay, what does that have to do with anything? Well, um, it turns out that Newton's gravity is instantaneous. Okay, that that's part of the understanding we have with Newton's gravity. Okay, so when we think about the Earth's orbit around the sun, um, we don't think, oh, it took 8 minutes for the gravity of the sun to make its way to Earth, like we do with the light of the sun, or at least that's not how people thought about the time. At the time, gravity was thought to be instantaneous, and gravity is a cause. Okay, so that doesn't reconcile with the speed of light being the maximum speed of causality, because instantaneous would be faster than the speed of light. So in order to really in order for his ideas about special relativity to be to be fully um, you know to be fully um, reconciled to gravity, Einstein thought he was going to have to generalize special relativity, and so he did. And as he pondered how to make special relativity more general so that it could factor in gravity, right? Um, he had what he called one of his happiest thoughts, and he had this he had several different versions of this thought experiment that kind of are can be referred to kind of collectively. Um, you know, and we're going to bring up a couple of different scenarios, and I think he himself had a couple of different versions of this basic thought. But this is the thought experiment Einstein came up with, at least one version of it. If we go back to the elevator we were looking at earlier, okay, on the left, okay, and let's suppose it's a stationary elevator. Um, let's now compare that to someone who's out in space, far, far, far from any kind of gravitational influence, just way out in the middle of nowhere, literally in space, on a rocket ship. But the rocket is accelerating at 32 feet per second squared. In other words, the rocket is speeding up, and it's speeding up at the same rate that gravity causes things to fall on the surface of the Earth. Okay, so person number one is on Earth in an elevator car that's not moving. Okay, person number two is in space on a rocket that is accelerating at at that same acceleration which something would be accelerated at on Earth if it was in free fall, if you just dropped it. Okay, so Einstein's thought was, if both of these people are in a closed compartment, so despite the picture um, on the screen that shows a window and everything, suppose there was no difference, right, between the two compartments the people were in. I suppose there are no telltale vibrations or anything that let you know you're on a rocket or an elevator. Everything's real smooth and everything's real quiet. If you're just inside your compartment, you would not be able to tell any difference in the physics you could do or see in those two compartments. Okay, now that's true even though on the left classical physics would say that's an inertial reference frame, because your motion is not changing, you're not speeding up, you're not slowing down, you're not being accelerated, even though you're in a gravitational field, because your reference frame is still it's in an inertial reference frame. And classical physics would say that the second case of being on the rocket that's accelerating is certainly not an inertial reference frame, because it is indeed accelerating and everything in the rocket along with it. Okay, but in both cases, if you were closed in, you wouldn't be able to tell the difference between the two. So you would observe the same physics. If you jumped, right? If you tried to jump in the elevator that's not moving, gravity would pull you back down, right? Whereas if you tried to jump in the rocket that's accelerating forward, initially you would manage to give yourself relative velocity um, compared to the floor, but then the rocket would continue to accelerate, and you wouldn't be accelerating. So in effect, the ground of the rocket would be rushing up to meet you, and it would be just the same experience you would have by jumping in the elevator. You would not be able to tell the difference. So Einstein considered this really, really significant, and he thought about it, from a couple of different angles. But the key is, in both these reference frames, one is actually inertial in classical physics, the other not. You observe the same physics. Um, Here's another thought. Let's say each person had a coffee cup in both reference frames. If you let go, it's going to drop, and it's going to appear to accelerate at the same speed. In the case of the first frame, the coffee cup is going to be pulled down by gravity at 32 feet per second squared. In the case of the second frame, when you let go of the coffee, it's going to stop being accelerated at 32 feet per second squared, but everything else that's attached to the rocket is continuing to accelerate and speed up during that time. So it's the floor of the rocket is going to accelerate up and hit the coffee cup with just the same apparent motion as the coffee cup in the elevator falling to the floor of the elevator. So Einstein was very intrigued by this. And we could even come up with similar comparisons, um, and see how they're kind of equivalent. Let's suppose that the elevator's in free fall on the Earth, so maybe it's a nice tall elevator shaft, but something happened and the safeties aren't kicking in, so the elevator's just plummeting, versus a rocket ship that's not accelerating. So now let's consider how these two situations compare. So elevator in free fall versus rocket not accelerating. Now, classical physics would say whether or not the rocket has velocity, because the rocket's not accelerating, in the last frame there, number 4, classical physics would now call that an inertial reference frame, and classical physics would say that the situation on the left, the elevator in free fall, would not be an inertial reference frame. So they've switched because it is accelerating downward. Gravity is a force that's pulling it downward. Okay, but Einstein realized that here too, the people in the situation could not tell the difference in terms of the physics. And if not for windows or vibrations or sounds or something, they would not be able to tell which situation they were in. If they just woke up in this situation, they would both have apparent weightlessness. In the case of the person in the rocket ship, way out in space, far away from any gravitational source, that makes sense. If the rocket's not accelerating, the person doesn't feel anything, pulling them in a particular direction. But that's also what would be experienced by the person in the elevator, which is in free fall. In fact, they're being accelerated by gravity, but they don't perceive it because in free fall, you don't appear to have any weight. And if you had that coffee cup again, and in both situations, people let go of the coffee cup, it would appear to be weightless as too and just kind of float around. So these two situations also appear to be the same to the people in the elevator, and the people in the elevator would observe the same physics. So Einstein, um, considering these sorts of situations, came up with what he called his equivalence principle between gravity and acceleration. Okay, um, in case one, stationary elevator, there appeared to be an equivalence to case two, the accelerating rocket. Likewise, in case three, the elevator in free fall, that appeared to be equivalent to a rocket not accelerating. In both of these cases, the illustration holds that gravity and acceleration are really equivalent things. And Einstein reasoned that light should also um, fit into that kind of paradigm. Light should behave the same in both cases, between the equivalent cases, so between 1 and 2 and 3 and 4. Um, and so he thought about what light would do. Okay, so let's put ourselves in the second frame, the top right, in the accelerating rocket. If we have a flashlight and we're shining it kind of transverse to our motion, so the rocket's accelerating upward, but we're going to shine the flashlight to the side. Um, in fact, the light would appear, not that we would be able, I mean, it would be so slight we wouldn't be able to notice because light is so fast. But remember, light's made out of little photons, and once the light leaves the flashlight, the little photons are not being accelerated anymore. So but the floor of the rocket is continuing to accelerate upward. The light would actually appear to arc a little bit, or put another way, if you shined a flashlight to the right, and someone just outside the spaceship could see it, they would see the light appear to be a straight line, but inside that straight line that they saw would appear to be a slightly curved line from inside the rocket ship because you're moving, okay, as the light travels. Okay, now the person on the stationary elevator would see exactly the same thing. Classical physics would say for a different reason, because the person on the elevator is shining a light, but the light is subject to gravity. So the little photons in the light are also bending downward. They're being accelerated downward, but the rate of acceleration is the same as the rocket ship. So both of these both of these flashlights, if you were able to track the exact path the light was taking, both of them would see exactly the same downward arcing um, light rate. Now, for the person on the rocket not accelerating, that's case 4, it's clear that light would, I mean, you can easily think that light should just travel in a straight line, straight to the right. Okay, what about the person in free fall? Would that match the person in the rocket that's not accelerating? It turns out yes, because the person in free fall actually is experiencing gravity, which will tend to deflect the light path downward, but their free fall is causing their entire point of view to also accelerate downward. And so the net effect of both of those things is they would observe the light to go straight to the right inside the elevator in free fall. So here again, situation 1 and 2 are equivalent, situations 3 and 4 are equivalent. Okay, now let's change it a little bit. Now let's consider what happens if you put the flashlight on the floor and you shine the light upward in whatever compartment you're in. Okay, so let's start with the rocket not accelerating. Okay, that's the easiest case. So if we put the flashlight on the floor and we shine the light upward, what we find is the light simply goes in a straight line and hits the ceiling and doesn't change. Okay, now let's consider what happens in the accelerating rocket, situation number 2. Same thing, we put the flashlight on the floor, we shine the light upward. Well, this time we're going to actually see a change in the light, and here's why. Because the source of the light, basically the floor, that's where the light comes from, the flashlight on the floor, the source of the light is moving at a certain speed when the light comes out of the flashlight. But after the light leaves the flashlight, the rocket and every part of it, including the ceiling of the rocket, is going to continue to accelerate. So by the time the light reaches the ceiling of the rocket, the compartment that the person's in frame 2, by the time the light reaches it, it's going to be going faster than the flashlight was going when the light was issued. So in other words, and it's going to be going faster in a direction that the light has to catch up with. So there's going to be a Doppler shift there. The light is going to shift toward the red end of the spectrum. Okay. Now, um, is this equivalent to what the person will see in case 1, the stationary elevator on Earth? Well, um, yes, it is equivalent, but it's not going to be a Doppler shift caused by um, relative motion. The source and the detector of the light being in relative motion. Now it's going to be caused because you're in a gravitational field on Earth. So you're in your stationary elevator. What happens is you shine the light up, but those little photons are losing energy as they have to climb higher in the gravitational field, because you lose, you have to give up some of your energy to get to a point where you have higher potential. That's true if you're a baseball or a photon. And if we take that into account, that means that the photons up by the ceiling of the elevator are going to have a little bit less energy, and in fact, they're going to. You remember the energy of a photon is equal to Planck's constant times the frequency. Well, that means their frequency is going to be smaller. In other words, there's going to be a redshift there too, except we call this one a gravitational redshift. Yet, once again, Einstein's right about his intuition. The person in the compartment can't tell which it is. The person in the compartment can't tell if it's, if there's a redshift because the rocket is accelerating upward um, at at you know 32 feet per second squared, or if they're in a gravitational field. In fact, Earth's gravitational field. In the other case, you just can't tell the difference. There's the same redshift. What about case 3? We haven't talked about case 3. Does it resemble case 4 again? Is it the same as case 4 again? Okay, case 4, rocket not accelerating, light's unaffected. It just shines out of the flashlight of the ceiling, no shift. Is that what we see? Is that what we see if we're in an elevator in free fall? Well, it turns out yes, but the answer is more complicated, because two things are happening. One thing that's happening is the light is losing energy as it fights against gravity in case 3, because you're on Earth, so the light feels the gravity after it comes out of the flashlight. The little photons feel the gravity, so they're losing energy to that. But the elevator is in free fall, so it's being accelerated by gravity downward, and that means there's going to be a Doppler shift toward the blue end of the spectrum. So the fighting against gravity, there's going to be a shift toward the red end of the spectrum. But because the elevator is falling downward, the ceiling has when the light hits it, has relative speed compared to the flashlight when the light left the flashlight. So there's going to be actually a blue shift there, because it's moving toward the source of the source of the light in relative motion. So those two Doppler, the gravitational redshift is going to be exactly canceled out in this case by the Doppler blue shift, or shift in the direction of the blue end of the spectrum. So yes, once again, the people in the rocket not accelerating and the elevator in free fall on Earth, they're going to see the light behave in just the same way. Now, we could have done a similar analysis if we wanted to put the flashlight on the ceiling and point it back at the floor, but I'll spare you that. We would have found out the same thing. So, having talked through all that, now it's time to introduce 4 identical light clocks. Same kind of thing we used before when we talked about time as measured on the train versus next to the train on the ground. So we're going to use light clocks here too and see what we can see. Okay. Well, clearly, the easiest case to understand is probably case 4, person way out in space, far from any source of gravity, in a rocket that's not accelerating. Okay, so their light clock is going to just work, to measure time, no special considerations. The light's going to bounce back and forth between the mirrors, and each time it goes one round trip, it's going to be a tick of the clock. Because that's kind of a simple case, we're going to compare all the other cases to this one as to whether or not time is flowing at a different rate. Okay, so number 4 is going to be our reference case. Let's think about light clocks in the other situations. Okay, so in the accelerating rocket, if they have a light clock, right, it behaves in the same basic way. They would continue to think that nothing was different themselves, but how would it compare to the situation in frame 4? Well, so when light, now we're talking about case 2, the accelerating rocket. When light issues from A, the mirror on the bottom, on its way to mirror B on the top of the light clock, the top of the light clock is actually accelerating upward and away from the pulse of light. So it actually ends up having to travel a little bit further to reach it. So it takes a little longer for it to make that half of the trip. Okay. On the other hand, once it bounces off the mirror at the top, mirror B, and it's on its way down to meet mirror A again, the mirror A is accelerating upward, and now is rushing upward to meet the light. So it kind of so the upward part of the journey takes longer, but the downward part of the journey for this one light pulse is going to take less time. You might think they would cancel out, but when we do the math, they don't cancel. The total trip it takes the light to reflect off of mirror B and go back to mirror A is going to be longer. It's longer. So what that means is time relative to the observer in the situation in frame 4, the rocket now accelerating, time seems to go slower on the accelerating rocket. Okay, so that's what happens. Now, here's where we try to make our comparisons to the other 2 frames. So now we know that there's time dilation on the accelerating rocket relative to rocket out in space away from gravity, not accelerating. How about situation 1, the stationary elevator on Earth? Does the stationary elevator in uniform gravity also experience time dilation like the accelerating rocket? Because that's been the pattern, right? Well, Einstein kind of wanted to say yes there, because he's thinking of the equivalence principle. So why wouldn't you experience the same sort of time dilation in gravity? Okay, but there's just one thing about it. There's no mechanism to explain with a light clock why time should actually go slower in a gravitational field. We can explain it with some fairly simple math. It's nothing more than algebra and some simple physics in the case of the accelerating rocket. In the case of the stationary elevator, there's nothing to account for. Well, nevertheless, Einstein is going to hypothesize that there will be time dilation in the first situation relative to the fourth situation, the rocket not accelerating. So that's going to be a hypothesis that Einstein is going to make, and we're going to explain that. So the details are pending. So it's going to turn out to be, yes, there is time dilation on the stationary elevator compared to being far out in space and not accelerating anywhere. Okay, what about the elevator in free fall? Will it be like its corresponding case, the elevator not accelerating. Does time flow in number 3 the same as in number 4? And now this is a little tricky. The answer is going to be no. It's not going to flow at the same rate. There will be time dilation there too, relative to situation 4. So to kind of sum it up, um, the only clock that isn't running slower than the clock on the rocket that's not accelerating way out in space is that clock itself. So it is what it is. All 3 other cases experience time dilation. And I'm going to even point out something surprising. Actually, the elevator in free fall is going to have the highest rate of time dilation compared to any of these. But we'll get to that later. The key thing now for us to remember is that the stationary elevator is going to be assumed by Einstein to experience the same time dilation as an accelerating rocket. There's no basis for him to say that other than the pattern he's noticed that acceleration appears to be equivalent to gravity. Well, let's shift gears a little bit, not to bug anyone, but how about taking a little spin? At this point, to get further in his thinking, Einstein had to come up with a new way to think about the relevant topics here. And so this is what he came upon. It's actually a variation in a thought experiment someone else came up with. But this is Einstein's version. Okay, now it's a little tricky to explain. Hopefully the picture will help, but let me explain it. Suppose you're sitting in the center of a metal disc, okay? And maybe it's like a amusement park ride. Maybe people can be on the disc and everything else too. But let's say you're sitting in the middle, and so you're an observer. And let's say initially when the metal disc is not moving, you put in a bunch of tiny little rulers all around the circumference of the ring. Okay, so you can actually measure, according to how many rulers there are, you can actually measure what the total distance around the ring is. And of course, you can also measure the distance from where you're sitting in the middle to the ring itself, which is going to have some radius value r. So what does our geometry tell us from school? It tells us that the distance around the ring, the circumference, which we're going to call c, it's going to be 2 times pi times r, 2 pi r. That's what the circumference of the ring is going to be. Okay. Now let's complicate matters just a bit. Suppose that we now gradually cause this ring to start to rotate around the center where the observer is, where the observer's pictured. So we cause it to pick up speed. We can measure how fast like the ring is going. If we were to turn that into straight line motion, we can measure how fast, and let's just say the tangential velocity of the disk is v. Okay, just some velocity v. So we spin up the disk, we get it spinning so that that the tangential velocity is v. That just means if something broke off, it would be traveling at the velocity v. Okay. What does the observer see now? Well, special relativity actually tells us what the observer should see. The observer will continue to see that the disk appears to be a radius r away, because that distance straight to the disk is not affected by the perpendicular speed that the disk is spinning at. Okay, so that distance won't be stretched or contracted or anything. It's just going to be whatever it is. But the ruler that if you're looking straight at the disk from the middle, the ruler's a different matter. because it's now moving at the speed v, special relativity tells us that we will have a case of length contraction. If you happen to be on board the disk spinning with it, the ruler will still seem to be the same length, but an observer in the middle um, will actually observe that the ruler seems a little shorter. Okay. Now, the person in the middle will continue to see the radius of the disk being r. The person in the middle, not moving, will still see a circular disk. So the person in the middle applying geometry will still be led to think that the circumference is 2 pi r. They will still see something that looks like the same disk. But because it's spinning faster and the rulers are shorter, the rulers no longer appear to cover the entire disk. Now it appears that there are little gaps that have opened up between the consecutive rulers, and so in fact, um, that's what's happened. Okay, and I'll try to explain that in a second. Um, but if you were on the disk, you would also notice that the rulers had that spaces had come between the different rulers that used to be touching. So what's happened is the disk has expanded in size as it's spun. You can imagine there are stresses and things. Well, they have to be there. It can be shown they absolutely have to be there if the thing is not infinitely strong with infinite mass. If you can spin this thing at all, this is going to happen. Okay, so little gaps are going to open up. Yet the key thing is going to be that the person in the center is not going to see it that way. We're supposing that the whatever whatever we're supposing that this disk has no choice but to have a fixed radius. So the person in the center is going to see the disk appearing to have the same side, but they're going to know, because the rulers no longer touch, that the circumference has increased. So while I guess the way to put it is, while the person in the middle still sees a disk of radius r with circumference 2 pi r, they know, because of special relativity, that on the disk the circumference has actually increased. So the actual disk has gotten bigger, and yet it appears to fit in the same amount of space. So this is the tricky bit now. The real disk, okay, the real disk, which is bigger, the person on the disk is going to continue to believe that they're distance r from the person in the middle, but they're going to see that the disk has in fact increased in circumference. So it's going to be the case where the person on the disk is going to believe that the circumference is not equal to 2 pi r, but greater than 2 pi r. Okay, all that to say, that doesn't work with Euclidean geometry. So we need a source of inspiration, and I'm going to go to Proverbs 6:6. In the NIV it says, "Go to the ant, consider its ways, and be wise." So we're going to actually think about ants in a way that's helpful here. Okay, this doesn't work in Euclidean geometry, the kind of geometry you learn in school. Okay, doesn't work. A circle always has a circumference that's 2 times pi times r. But if we pretend we're an ant, I think we'll be able to make some progress here. To an ant, whether you're on a flat sheet of paper, which is like a two-dimensional flat surface, which Euclidean geometry handles just fine, right? Um, you would be able to march along the little paper, and everything would be swell as far as geometry. But if you put an ant on a curved surface, right, it's still, mathematicians would still say it's a two-dimensional surface, but it's curving in three-dimensional space. If you put the ant on a curved surface, uh, Euclidean geometry would not hold. And let's think about why that is. Um, if you're on a spherical surface, you could if you're a little ant, you can march around a circle on the surface of the sphere, and you could also go from the um, circumference of the circle inward to the center of the circle. But because your radius would kind of be arced, right? It would actually be a little bigger than you would expect in Euclidean geometry for the circle. You would find that your radius was bigger than you would have thought based on your circumference. Or put another way, the circumference will be smaller than 2 pi times your radius. Because the circle, you can almost just think about slicing off the top of the circle from the sphere. And if you flipped it over and looked at the flat slice, it would be no different than the paper on the left. It would be handled with Euclidean geometry. That circle would have a radius that's 2 pi r, but that's not the radius you would measure as a little ant, because the sphere is round. It takes longer to get to the center than it would if you were on a flat sheet of paper. And so in this kind of curvature, the circumference is actually less than 2 times pi times r. Okay. Now you can also curve a sheet differently. Okay, it looks like a Lay's potato chip over there, but on the right, the same kind of thing. Let's say we start with a piece of paper like we had, but we're able to stretch it. Okay, we're able to stretch the piece of paper, and so we cause the ends of the circle to flip up, and we call left to right, and the ends like back, back front and back, we kind of tilt down. So we're stretching this piece of paper. Well, to an ant, it still appears to be a circle. The ant can still walk around this circle, but once again, in all this stretching, the radius has become, okay. So what's going to happen is, let's say we keep the same radius, but we actually are stretching the perimeter of the circle. Let's say that's what we did, just to keep it simple. So we keep the radius in place, and then let's just say we stretch left to right. What the ant's going to observe is, if the ant walks around the circumference, the ant's going to see a circle. Because if you're hugging the paper like the ant, everything looks flat. You're going to still see a circle, but when you measure the radius and you multiply it by 2 pi, you're going to find that the circumference is actually bigger than that. Okay, so this circle, this apparent circle, has a circumference that's bigger than 2 pi times its radius. And that's because, the curvature of the space it's in. So the bottom line here for us is we're kind of like the ant. Our apparent 3D reality seems to curve in another dimension. Now, we can't picture that other dimension any better than we could picture a third dimension if we were an ant on a piece of paper and we can only see right in front of us, right? But we're kind of like that ant. Our 3D, our what we would call our Euclidean three-dimensional reality as we perceive it, is actually curving in a fourth dimension. And so these examples of two-dimensional surfaces and everything in the ant are just a way to try to picture that, because our minds can't really see in a fourth dimension. But Einstein turned up evidence in his thought experiment with the disk that it must be this way. Okay, so and by the way, not only did Einstein perceive that our three-dimensional reality actually has another dimension to it, but he also observed that someone on the disk would be experiencing centrifugal force. Just like you're on one of those amusement park rides, you would experience what some people call artificial gravity. You would be pressed back against the outer wall of one of those spinny rides, whatever they're called, and so that caused something to click with Einstein. He said, I wonder, I wonder if gravity could possibly correspond to the curvature of space. And that turned out to be the critical insight for Einstein, right? That was his critical insight. He called it a decisive idea. So he took that idea along with the equivalence principle, which is that gravity and acceleration seem to be equivalent, and he figured out he wanted to see if he could work out a geometry um, where that would actually be an explanation for gravity itself. Okay, and we'll see more as we go what he was thinking. Where gravity stops being a force and starts becoming geometry. So he was he realized when he set out on that journey that he would actually need to study whole new areas of math that he did not know. And Einstein was, pretty well educated by this time. He was a pretty solid mathematician, and he had to actually get some mathematicians to help him because it was a difficult area of study. But eventually, he was able to derive equations that were very concise, complicated but concise, deceptively simple looking actually, that described what we will now call general relativity. And in fact, not only did he generalize special relativity, but he came up as part of that with a whole new way of looking at gravity, which is why general relativity is often called Einstein's theory of gravity. And we're going to talk about the details as we go here. But before we get too far along, let's just briefly step back to um, our scenarios, our four scenarios, and our light clocks here, because we have a couple of outstanding explanations we need to make. When we thought about the behavior of the light clock on the stationary elevator versus the accelerating rocket, we said yes, but there wasn't any apparent mechanism for that. Well, now we're going to say yes, this is a core hypothesis built into Einstein's theory of general relativity, which has now been, not to spill the beans too early, but now it's been experimentally proven to high precision. So it turns out that that the theory of general relativity explains why this the rate of time would pass the same for the stationary elevator as for the accelerating rocket. That's just a key part of it. Einstein was right. It's been proven experimentally. In the case of three, situation three, the elevator in free fall, the pattern was it always matched the situation um, next to it, situation four, rocket not accelerating. Um, and we said that in this case, the time flowed at a different rate. Okay. Um, well, um, again, looking at it from Einstein's theory of relativity, we know there will be time dilation because even though the person in the elevator can't sense the gravitational field, they are in a gravitational field. And just like in situation one, they're going to have time dilation as a result of that because they are in a gravitational field. Furthermore, because the elevator is accelerating downward because cable's broken, gravity's pulling on it, and it's picking up speed. Because it's accelerating, it's also experiencing a degree of time dilation, just as in case two for the accelerating rocket. So it experiences time dilation both because it's in a gravitational field and because it's accelerating. Doesn't matter what direction it's accelerating in, it's going to experience it. And and so it's actually got more time dilation relative to the rocket not accelerating in situation 4 than the other two situations. Here's the thing, though. Even though that's true, it remains the case that the person on the elevator in free fall cannot discern any difference in physics between the person who's on the rocket way out in space not accelerating, because neither one of them are able to see each other's clock. They're both in their closed compartments. So still the physics that you can do, the laws of physics that you can see in 3 and 4 are going to be the same. But in fact, if you were able to compare the rate of time in 3, it's going to pass slower than in 4. And it's going to pass even slower than it does in 1 and 2. Okay? So with that, we can continue. So Einstein actually published his general relativity in 1916. And basically, his equations at the bottom there have been summed up this way. Very famous quote on the left. The equations basically say this: space-time, because it's like one four-dimensional thing, space-time tells matter how to move, and matter tells space-time how to curve. Okay, so to put that in a little more explicit fashion, this thing we call space-time, which we've been thinking about since we've done special relativity, because it's clear that if you're going from one reference frame to another, you not only have to convert your coordinates but also your time. It's like this, so it's like you can't just consider position independent of time. This thing called space-time is a curved space, and that's going to determine the path that something will take if it's in free fall, right? If it's not, if it's moving in an inertial way. We'll talk about that in a second. But why does it curve the way it does? Well, because the matter that's there, has has an effect on space-time. It causes it to curve. Okay, so that's what the theory of general relativity says. Now let's start with the bullet points at the top there. So go through this just in a different way. Relativity, including special relativity, shows that time and space are kind of coupled together. So our time coordinates and our spatial coordinates get coupled together. And likewise, what general relativity shows us is that mass and space are kind of coupled together. They affect each other. So big part about general relativity is it tells us that time ticks slower where we're in a greater gravitational well. Okay, when gravity is stronger. So the stronger gravity is, the slower time will tick. As long as you're somewhere in this universe, you can be. Okay. I'm not talking about the center of a black hole, if you've heard people talk about such things. But as long as you're outside the event horizon of a black hole, we would say that the time ticks slower the more gravity you have. Okay, and gravity is going to turn out to be the very way that this four-dimensional space-time curves. Okay, we don't perceive the curvature, we see only the spatial dimensions, but gravity, in fact, space-time geometrically curves, and gravity is the curvature. So what that means is gravity is not an actual force. It's not just another force, and it doesn't accelerate anything. Gravity is just curvature, local curvature. So where you are, the quote-unquote gravity that you experience is just going to be entirely based on the amount of curvature of space-time in that place. Okay, so uh, it should be pointed out that this deals with Newton's discomfort over gravity acting at a distance. Now, gravity is simply a consequence of simply a consequence of the curvature of space-time in the time and place where you are. Okay. Now, um, if you're not accelerating in a curved space-time, you're simply going to continue in a straight line. And there's a special name for that. It's called a geodesic. But like whether you're a ball thrown through the air, if we ignore air friction, or you're a planet orbiting around a star, you're just falling around the star, or you're just in free fall in an elevator. In all these cases where you aren't being affected by any force other than gravity, and we just said gravity is not a force, so really we could say in any case where you're not being affected by a force, you're simply going to follow the geometry of the situation. That is the apparent source of gravity. Okay, now all this has been all this and all its predictions, which include things like gravity waves and uh, and other things that are more subtle, even, and we're going to talk a little about those. All those things are consistent with observation and experiment, and so we're going to talk a little bit about those in a moment here. But I do want to call your attention to something. Back when we studied Newtonian physics, Newton's first law, in the form we saw it in, was bottom left over there, uh, which is called the law of inertia, says an object remains at rest or in motion unless a force acts on it. And that is correct. Um, and so it was fine. But I want to be a little more explicit here, so we can notice something important. Um, or at least I'm going to try to say what I had said a few minutes ago in a way that hopefully registers clearly. Okay, a more explicit way to talk about the first law is the one on the right, the one that says an object remains at rest or continues to move with uniform velocity in a straight line unless acted upon by an external force. That's just the wordier version of number one, but I like it. I think it's useful for us right now to understand that Newton's first law basically said that unless you're acted on by a force, if you're in motion, you continue in a straight line at whatever your velocity is. Okay, whatever your speed is in the same direction. Okay, and the reason I want to point that out is basically Einstein's idea of curvature taking the place of a gravitational force means that when you're responding to um, gravity, right? When you're responding to gravity, it's just because you're moving in what to that little ant walking on a curved surface would appear to be a straight line, because you appear to be going on a straight line. And it's just that the contour of space-time, right, is actually curved, and your straight line actually looks like a curve if you perceive space to be, what we call flat or Euclidean. Okay, so that's what general relativity really is. It takes a little thinking about, but so Einstein's law is just that gravity is not a force. It's just basically you're following the first law, and if other forces act, well, then they can shift you in terms of where you're at in space time, but you're going to tend to go in a straight line at a constant velocity, just like we talked about all the way back with Newton's first law. But that assumed a different kind of geometry for space. Okay. So we encounter our little gravity guy again, our cartoon figure, and now that we've reached this point, he said, yes, that's the real me. And he's saying, I'm the very shape of space and time. But, he says, I'm also a good listener because I respond to matter and energy. So, yes, just me trying to be funny. Um, because mass and energy tell space-time how to bend, gravity really is the curvature. So, gravity kind of is a good listener. It does change its itself, which is to say the curvature of space and time, based on matter. But then it's that curvature that causes things to seem to move under the influence of a gravitational field. Okay, so that is, in a nutshell, general relativity. And um, I'd like to talk a little bit about the different confirmations we've had, because it's based on thought experiments and it's based on math and everything, but it's not necessarily obvious that it has to be true. So you have to test things in science. We'll talk about some of those confirmations in a bit. But before we do that, I wanted to try to visualize, um, this idea of curved space-time a little bit more, where space and time bend according to like how, like the location of matter and energy in a particular region. So let's go to a thought experiment of our own. Okay. And don't confuse this with the earlier case. It just occurred to me while I was preparing. This might be an easier one to illustrate. Let's suppose we have a massive spinning disk. Now, before, um, our assumption was that it was kind of light and the mass didn't matter very much, and we weren't taking into account what we're about to take into account here. So you have a massive spinning disk. Let's just say it's a very, very massive disk. Maybe it's a very heavy disk, and let's also say maybe it's going fast enough so that it has its relativistic mass is very high. Um, what would space look like? What would space look like? Space time look like around this disk? Okay. Well, now, it's essentially a two-dimensional shape, so we can't really picture a three-dimensional, space being curved into the time dimension very well. But maybe because this is kind of two-dimensional, we can kind of imagine what the curvature must be like. And it would turn out to be kind of like this. Where is kind of flat, you would not experience any gravity. So notice in the center it's kind of flat, and then way out away from the ring it's kind of flat. But this disk is very massive and energetic, and where the ring is, you would actually see a curved space there. Okay, so although spatially, just looking at the spatial dimensions, the radius to the disk would appear to be r, in space-time, um, the actual curvature is a little bit, the actual radius will be um, a little bit larger. Okay, so here we see r prime, which would be kind of the actual radial um, um, extent from the center of where the observer is down to the ring. I should say that this is just an illustration, and this is supposed to be illustrating space-time. So it's true that the spatial dimensions would actually have some curvature as well. So you might you might the observer might actually think that the circumference of the massive disk can change. But this is kind of what the space-time curvature would look like if we're just thinking two spatial dimensions in the time dimension. And I did say that away from the disk it flattens out, and it kind of does, but it's not totally flat, and that's because someone outside the disk would tend to be attracted by this massive object. Okay, if you get far enough away, it gets pretty flat. But hopefully this helps us to picture a little bit what space-time curvature looks like. I should remark here that once again, um, it's not only space that's bent, time is bent. In other words, it's not only the lengths of spatial dimensions that are affected, but also the rate at which, or it's also the, kind of time itself can be stretched and be kind of longer or shorter. Okay. Um, and I'll point out that these sorts of effects can be significant. Okay. The Earth doesn't have um, so much mass that it distorts space-time um, in a way that's particularly amazing in this regard. But if you measured the the actual distance to the center of the Earth, right, it would be a little longer, right, by 1.5 millimeters than what you would think it should be based on Euclidean geometry. But the sun, much more massive. If you could actually um, make a similar statement, except now it would be 3 kilometers. So the radius from the surface of the sun to the center is going to be 3 kilometers longer, just because of the uh, stretching or the curvature in space time. Let's try to be a little more general with our visualization. Kind of like we just saw, a lot of times people will put like grid lines or there are a couple different strategies of trying to illustrate how there's curvature in space-time. Okay, so they often, different drawings use those kinds of things. Um, like on the left there, we see an example. If you've got the sun, you got the Earth. The sun is very massive, so it looks like it's kind of curve, causing the kind of the square grid representing space-time. It's kind of causing it to curve more, and the Earth is not quite as massive, but it's causing it to curve somewhat too. But I'll tell you, in terms of our three-dimensional spatial reality, I think it might even be helpful to picture um, things like on the right. This is like a 3D lattice, and if you want to think about it this way, let's say everything, let's say you had a perfect cube, you had a perfect lattice of little cubes, all perfectly straight and everything. And let's say they all had little clocks on them. It's a little hard to see the little clocks, but at each corner there's a little clock dial. So all these little cubes would indicate like a unit of length in each direction, and the clock would indicate how fast time is moving. Okay, but when you put something massive like the sun into a region of space, and that's the bright object pictured at the center of the lattice, in the case of the picture on the right, it would actually cause a distortion in those spatial dimensions that are represented by the cube, the lattice lines, but also the little clocks would be affected. Okay, so that's really what general relativity says. Okay, and all this is very qualitative, but remember, Einstein came up with equations. He came up with math that's been confirmed and everything. So this is not just qualitative, but that's another way to picture how space and time are distorted because of mass and energy. Okay, and and also what space-time an object sees um, that that we sense as gravity. Okay, here's another illustration on back to the left. Um, this shows a little bit different strategy of laying out the grid lines. They're kind of more radial. This one's kind of good because it pictures the Earth around the sun. It's not completely realistic because there should be a little pucker, a little dimple where the Earth is. because it has mass, and it would also affect the space-time. But what I like about is it shows that what we perceive as the Earth orbiting the sun, because of a gravitational force, is just the Earth following what looks like a straight line. If you can imagine, instead of the Earth putting our little ant there that just is going to march straight ahead, just follow the line straight ahead. In effect, that's why that is equivalent to the Earth's orbit around the sun. Remember, that was called geodesic. So, um, you know, that's one way to picture it. You can imagine something like a ray of light coming in, and if it's like a little ant just marching, you could imagine it dipping into the sun and then dipping out. So that's another way to visualize. Um, Sometimes physical analog can help. Okay, sometimes it's nice to see something in motion. So there's a way to visualize this. Here's a
Okay, so
little
this is the
you.
gravity well. Give it a whirl with some marbles. There we go, they got one orbit in there. Two, three moons maybe around the planet. You can add other masses, have more complicated systems. But there you go, the gravity well.
Okay, so this is another way to visualize how things move under the influence of curved space-time. So you see there that central object that's been dropped on the rubber sheet. Um, when you put other objects on the rubber sheet, they're just going to follow the rubber sheet, and that's going to cause them to take certain paths. It's not because of the quote unquote gravity of the thing that's been placed in the middle that's pulling them into the circular orbit or something like that. Of course, it's an imperfect illustration because it has friction and the things slow down and everything. It's also an imperfect situation because the reason they roll around on that rubber sheet is because of gravity in the first place. So it's kind of it's just a visualization. It's not physically the same. Well, hopefully all that helps, and we can move on and look at how general relativity held up in terms of testing, and and how it was useful in physics and astronomy. It turned out that general relativity uh, was correct when it came to describing space. Um, Early on, um, Newton was considered a genius because he was able to explain why the planets move in elliptical orbits around the sun. But his analysis was a little simplified, and it was a good approximation. But what he did was he considered each planet going around the sun separately, and he did not consider the gravitational attraction between the planets themselves. It turns out that once you try to do that, you have a more complicated situation than you can find exact paths for using straight math and Newtonian physics. Although you can approximate as well as you want with a computer or just hand calculations, um, but it turns out that the actual orbits in the solar system are more complicated um, than Newton's description of the orbits originally, as good as it was. So one thing in particular that changes is the orbit of Mercury. And over on the left, you can kind of see a picture. And what this picture represents is it shows that every time Mercury goes around the sun in an elliptical orbit, um, where Mercury is closest to the sun shifts each time a little bit. Okay, so Mercury still goes around the sun in an elliptical orbit, but the point of closest approach, which is called perihelion, um, it shifts, and that shift is called a precession. So Mercury's orbit kind of precesses around the sun as it orbits, uh, you know, time after time. And if you apply Newtonian physics to try to address this um, particular situation, um, you could understand why the orbit does this because of the other planets. You could factor those into your calculations, and you would get that the orbit would precess or shift like this over time, but it wouldn't be the right amount. It wouldn't be the right amount. Einstein applied general relativity and showed that he could explain the right amount of shifting. He could explain using his very general equations. They exactly predicted how the orbit of Mercury should shift over time. So um, Einstein's theory of relativity, even for things that were kind of well understood in physics, turned out to be a better description of reality than Newton's law of gravitation. And there are a whole host of more subtle effects, space-time effects that are built into those equations, and to the extent they've been tested, um, some of them are hard to test, but everything that's ever been tested tests out pretty well. So general relativity is correct about space. Okay, it turns out that general relativity is correct about light. We in our thought experiments we considered how light would be affected in different reference frames, and indeed, it turns out that light is bent by gravity, and we talked through that. But that's part of what general relativity says. Except, just like a ball or anything else, a light particle, a photon in general relativity is just going to, if there's no other force on it, which light doesn't really interact with forces, it's just going to follow the geometry of space-time, and that has been confirmed. Also, the idea about the gravitational redshift, the fact that the light would have to would have to climb out of the gravitational well, um, that's confirmed by general relativity, or that's confirmed by experiment as well. Um, even more recently, we've been able to look far out in space, and we've been able to see that in cases where there are some large, massive objects between us and something else, that we do see a gravitational lensing effect, and that is also as predicted by general relativity. Specific experiments have been done and enable us to say that general relativity is also correct about time. And that's one of the weirdest parts of it. So, yeah, that's really valuable to talk about. General relativity is correct about time. So, they've actually launched special purpose satellites to try to detect the difference in time between Earth and somewhere out in Earth orbit, which is further outside the gravitational well of Earth, even though it's in free fall, and they were certainly able to test it. Um, in fact, with our GPS satellites in orbit, um, those things work by broadcasting signals, and then your phone or whatever picks up signals from different ones, and is able to determine your location. Well, it turns out that if you didn't correct the little signals also have a time stamp on them, which enable you to understand how where the satellite was when it sent out the little pulse that your phone just picked up, and that timestamp has to be adjusted to fit the clock speed on Earth, the rate at which time flows on Earth, or you would not calculate the right coordinate system. The GPS system would get off really fast if they didn't take into account general relativity's effect on time, which is to say, the effect that gravity has on time. Um, NASA has to account for the difference in the flow of time whenever whenever they're dealing with things on the moon or things on Mars because the gravity is different there. Time flows differently on the moon and on Mars. Not by a lot, but some. Okay. In fact, these days it's remarkable, but we actually have some very, very precise clocks called atomic clocks, and they are so good that they can even pick up the difference in time flow depending on what shelf you put them on. So you can raise or lower an atomic clock by as little as 33 centimeters, and you can actually measure a different passage of time, which is amazing on the one hand, and on the other hand, uh, the basis of the little comic strip, the little picture, the comic picture on the left there, where it shows two guys at the National Institute of Standards and Technology, and one's hanging his clock on the wall, and the other's looking at his clock on the wrist, and they're disagreeing. Because the funny thing is, actually gravity would flow at different rates depending on which location you're in, because the further you are from the center of the Earth, the less of its gravity you experience. It's not very much different by 33 centimeters apart, but enough so that atomic clocks can actually test the different rates that time is flowing. Well, general relativity was also correct about black holes and gravity waves. Um, the concept of black holes was actually imagined all the way back in 1783, before anyone knew anything about special or general relativity. Just thinking in terms of Newton's gravity, and also going on Newton's theory that light was made out of small particles, someone thought that maybe indeed something would be large enough to prevent light from escaping, um, if it had enough gravitation. But Newton and general relativity, it turns out, have singularities, mathematical places where the formulas for gravity doesn't work in their descriptions of gravity. And nevertheless, we can say that general relativity describes black holes very well, according to all that we've seen and observed. Um, in terms of what we can tell, insofar as general relativity says it, we've seen that that's the way these things actually work. We've seen a number of black holes in recent years imaged directly. Also, we've been able to pick up black holes uh, based on gravity waves. A lot of times these gravity waves occur when large massive bodies like neutron stars or black holes, or a combination of those sorts of things, actually are spiraling into each other and colliding. And because each one of them creates, um, you know, a different warping of the of space-time. Um, when they do circle each other, they send out little ripples throughout space and time, or I should say throughout space-time, which can be detected now on Earth. Einstein thought it would never be possible, but it turned out it became possible. It's basically an interferometer, not unlike the Michelson-Morley experiment, that enables us to detect these ripples in space-time. It actually changes the length along one of the beam lengths of the experiment, so that a detector can pick up kind of the difference. Um, so you basically split a light into two beams, and if in one dimension you're a little slightly compressed and then uncompressed a little bit, corresponding to when a gravitational wave passes through, because that's really space-time getting a little bigger and a little smaller in certain areas it passes, then that'll change the the path traveled by the two wavelengths, and so when the wavelengths are combined, you get a little bit of an interference pattern, or you see that the waves are canceling out and then adding together, and then canceling out. You can kind of see the wave passing through because the waves don't add up the same for a while. Um, And so, yeah, there are several facilities around the world now that can measure these gravitational waves. And they tell us a lot about the actual collisions between these heavy bodies, these neutron stars and black holes, or black holes and black holes. And all of it seems to be fairly consistent with general relativity. And not to mention, we can observe the universe now in many different wavelengths of the electromagnetic spectrum. Visible light, infrared, microwave, radio waves, even X-rays and gamma rays, and but now with all those we have gravitational waves that we can use to observe astronomical bodies. And so some people have termed this the era of multi-messenger astronomy to handle all these things. There's another addition to that too. One of the particles we didn't talk about much last time, but yes, we're starting to see the universe in terms of its neutrino emissions as well. So now we have more and more ways to see the heavens, and some of those ways give us unique perspectives that were blocked before. So general relativity has made it possible for gravity waves to give us a new way to look at the universe. And general relativity has proven itself um, indispensable in cosmology. The title here says correct on cosmology, um, although I think that's a little more debatable, because in fact general relativity um, is mainly the framework on which modern cosmology is built. Certainly also takes information from quantum mechanics and the rest of physics and astronomy, but general relativity is really our most powerful tool for understanding what's going on with the universe. And what do we understand is going on or has gone on with the universe from general relativity? Well, directly from Einstein's original equations, it was found by Lemaitre that we lived in an expanding universe. Einstein, shortly after releasing general relativity, actually introduced a fudge factor, which wasn't motivated by any proof or anything, into the equations, which he called the cosmological constant. You can see the second equation on the bottom um, is um, is one that includes the cosmological constant term. Um, anyway, he did that because general relativity does, in fact, kind of force us to live in an expanding universe. But in his day, most scientists, including Einstein, thought the universe was eternal, and that the universe was what was called a steady state universe, meaning it didn't substantially change in its basic nature over time, even though things moved around and got shuffled, that it had always been. Because the alternative was it must have come about at some point. There must have been some point when the universe had a beginning. And having a beginning goes quickly to the question of how did it begin, or really what caused the beginning. And that's a question that most scientists prefer to sidestep and just to assume the universe was eternal. Well, shortly thereafter, Hubble discovered that, well, he discovered other galaxies. At first he thought they were other quote unquote universes, but eventually they realized they were seeing other galaxies. And the further away the galaxies were, the more the galaxies were redshifted, which ended up being attributable to the fact that literally the universe had been expanding. And because of the expanding universe, there was a redshift going on. So it wasn't a redshift caused by relative velocity. It wasn't a redshift caused by gravitation. This was actually a new kind of redshift called a cosmological redshift, which is what you would expect if general relativity was correct about an expanding universe, because as it expanded, the wavelengths of the light on traveling for vast distances would actually get stretched out as well, and that's exactly what Hubble saw. In the class, we have a bit of a, you know, an activity, but I'll just describe it here. If you put a bunch of dots on a balloon and blow the balloon up, you basically will find out that all the dots are getting further away from each other. And the only reason that can happen is if the surface of the balloon is increasing. It would be possible for two galaxies to get closer together and a few and yet further from some other galaxies, but when all the galaxies are flying apart, you know that space-time itself is expanding, and perhaps that's something I should have emphasized more this whole lesson. Um, the fact is that before the universe existed, according to everything we know, it's not like there was empty space and then a bunch of stuff exploded into it. It's that the empty space wasn't even there. So when we talk about the universe expanding, we don't mean that somewhere, in the vacuum of space, there was a big explosion that scattered all the stuff of the universe in every direction, and it's just been flying outward ever since. What we mean is that there was no place before. There was no there were no locations before. There was no space before for anything to be in. Then all of a sudden it came into being, and since that time it's been expanding. Because of Hubble's discovery, Einstein called the cosmological constant one of his biggest mistakes. It was just a quick attempt to literally insert a fudge factor into his field equations to observe the possibility of a steady state. But, you know, it's okay if we just let it be zero, and then we'll have the original equations. I should say that it's actually gotten recycled in recent years because, um, and hopefully we can talk about this next time, um, recent discoveries about um, the quantum vacuum and also something called dark energy um, means we need those terms after all. So they've been recycled to fit an actual situation in physics that is motivated rather than based on what scientists prefer to believe in the moment. So basically, general relativity gives a consistent picture on cosmology and predicted before it being discovered by Hubble that the universe is indeed expanding. And that was the exercise. Okay. Quick mention of the cosmic background radiation. For those of us who remember pre-digital television, if you turned on your TV and either the local television stations weren't broadcasting because it was too late, or because you were on a channel where there wasn't a broadcast, you would see this white snow. Turns out that corresponds to what we now call the cosmic background radiation. Um, this is the radiation that 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 was the first electromagnetic radiation that was visible in the universe. It's understood to be, at least, um, and it's been redshifted by the cosmological expansion all the way to the microwave region, and we can still study it. And so some people have called this a baby picture of the early universe. Um, it, um, it reinforces general relativity experimentally. It bolsters it, but general relativity and the cosmic background radiation together uh, make a very strong case about the beginning of the universe, because what can be seen by looking at this background radiation that's coming from everywhere in the sky is how uniform it is. This picture is it actually it actually is color coded so that it causes even the slightest differences to show up strongly. But in fact, this radiation is so close to uniform, coming from every direction of the universe, that uh, basically physicists believe the early universe must have been it must have been very densely concentrated and able to come to thermal equilibrium, basically to have a similar energy state before rapidly expanding and becoming the universe we see today. And so this is this kind of underpins the rapid expansion of the universe from a common origin. Well, at that point, I'll just throw up a picture here of what's the current consensus model in physics about cosmology, and it's called the lambda CDM model. And the lambda stands for dark energy, as reflected in the cosmological constant recycled in Einstein's field equations, and CDM stands for cold dark matter, which we have not discussed, but also factoring in general relativity and all the items we've talked about today and many more. This is the model that people have for the universe. At least this is the model physics has a consensus about, more or less. Lots of variations. Some people argue, this small change or that small change, but this is pretty much the mainstream of physics today. And they think the universe is around 13.8 billion with a B years old. So, you can look at this yourself if you want. You can Google it, lambda CDM. I imagine we'll talk about it a little more next time. But I've put up our key verse from today's study to compare alongside this thing. Again, from Isaiah 40, verses 21 and 22. Have you not understood from the foundations of the earth? It is he who sits above the circle of the earth, who stretches out the heavens like a curtain and spreads them out like a tent to dwell in. Well, the idea of stretching out the heavens and spreading out the heavens like a tent to dwell in, that's very consistent with the cosmology physics has put together, using general relativity and other ideas. The idea that not only did the universe come from basically no place, but also that the universe came out of nothing. It's very consistent with biblical creation in that regard. So next time, let's look at how other details might or might not line up with Scripture. We can talk about it. It doesn't just say in Isaiah, he spreads out the heavens. It says like a tent to dwell in. There's a whole other set of topics that we can discuss for next time, because in fact, this universe, as we see it, in terms of its laws of physics and many other factors, this universe is uniquely ideal for life as we know it, or even life as we can imagine it. So, if as some believe this is a random happening and it all just unfolded this way apart from any design, it's kind of hard to understand that, and we can look at that next time. Generally, that falls under the category of what most people call the anthropic principle. And what is this dark matter and dark energy stuff that we're just briefly encountering now at the end of this discussion? It seems to be part of the consensus model in physics about cosmology. What is all that about? We can talk about that a little next time. And where's it all going? There's the question of the creation of the universe. There's also the question of what the ultimate fate of the universe is. Physics has some speculations in that regard, and we might even line those up with some Bible verses too. So, all that said, hope to see you guys next week. That's the end of today's lesson. Thank you for listening.